Started when we last spoke. I showed you some integration techniques to derive the moment of inertia. I did a rod about its end, then I did a rod about its end using the parallel axis theorem. Uh, I also did two discrete masses from different parallel axes, but not using a parallel axis theorem. And then I did a cylinder as a continuous piece of matter and calculated that it's 1/2 mr squared. That's not unlike the example that your book gives where they do a hollow cylinder. So it's a cylinder missing a cylinder from the center. I'm not going to do that one. That's more or less identical to the one I did, except you go instead of integrating from r equals 0 to big R, you're going to integrate from r equals r1 to r equal big R or r2 or whatever. So it's really no difference there. I need to go ahead and get started in the dynamics portion of chapter 10. So let's go ahead and get that started. I'm going to go ahead and share my screen and make sure everybody goes ahead and chats me your first and last name if you haven't done so already. It looks like most people did. So here's my iPad screen. It's coming up. I've went ahead and written up the first example that I'm going to work. And this is an example I made up and I do it for my students every semester. So it's just called example as opposed to example 10.2 or something because this one's made up. So what I said is an Atwood machine is made with a cylinder of mass. Oh, I need the word A there. With a cylinder of mass capital M and radius capital R mounted on nearly frictionless bearings. On one side hangs a mass MB for big mass, and on the other a mass lowercase m. Those masses are secured at the opposite ends of a massless string that will not stretch, get slack, nor slide along the cylindrical pulley. Calculate the tensions TL and TR, the angular acceleration alpha of the pulley, and the linear acceleration A of the hanging masses. So that's the project that we're trying to work through in this case. I've already drawn a picture of the diagram. Now I'm gonna draw the free body diagrams. So first off, it looks like the way I have it drawn, notice the MB is the big mass and it's really high. So that's in suggesting that it's going to rotate counterclockwise and the mass on the left is going to fall down and the mass on the right is going to lift up. So I'm going to choose all those directions associated with positives so that I don't have to have some weird equation like A equals negative R times alpha or some stuff like that. So I'm going to explain to you how I choose these coordinates, and you just got to remember to do that, or else you're going to have to add these spurious negative signs all over the place. So let's start off with the free body diagram for mass m sub b. So right here I have a mass m sub b. Acting on it, of course, is a weight mb sub g acting in the downward direction. That is with a coordinate that I'm calling down as the positive y coordinate. And of course, acting upwards on it is a tension, and it's the tension on the left side of the pulley. So I'm going to write this as TL. Now, if you're thinking about this way, if you imagine the TL on the left-hand side, the TL on the left-hand side has to not only lift lowercase m up, and accelerate it upward, it also has to rotate the heavy pulley so that the tension on the left should in fact be larger than the tension on the right. That's why I have to describe them as TL and TR. If the pulley was indeed massless and frictionless, this one's frictionless but not massless. But if the pulley was massless and frictionless, then T left and T right would be identical. So that's a big difference here. Now you see that I've got the positive y direction is down on the left. That's going to correspond to up on the right, and it's also going to correspond to a counterclockwise rotation about the axis coming out of the page for the pulley. So with this free body diagram, I can go ahead and write the summation of the forces in the y direction equals mass times acceleration in the y direction. And for that reason, I'm going to say that my equation is mb minus T sub L is equal to mb times A, and that's going to be equation one. Now I'm going to do a free body diagram for the actual pulley. And there's my pulley. And the way I have it drawn is I am going to say there's a torque caused by this tension right here. So this is the force T sub L. And of course, the radius of this is just big R. But then in addition to that, I have another tension pulling down on the other side, and that one's T sub R. And of course, that side also has a radius of R. And for this one, we're going to say the summation of the torques is equal to I times alpha. Notice that the actual tension comes off the pulley perpendicular to a radial line so that R cross F is just R times F in this case. So not only that, I'm keeping this rotating clockwise or counterclockwise as the positive direction. So that means the TL is going to be the positive, cause the positive torque, and the TR is going to cause the negative torque. So this is going to be TL times R minus TR times R is equal to the moment of inertia for a cylinder is 1/2 mr squared, and then all of that times alpha, which is something that we're ultimately going to be able to solve for, and this will be equation two. We know we have unknowns T, L, T, R, that's two of them, A and R, that's four of them total. So we're going to need four equations. I'm going to go ahead and do a free body diagram for the mass little m now. So for the mass little m, we're going to have a mass right here. There's little m. And up on this side would be the positive direction. So I'm going to say that acting on this side is a tension T right, or T sub R, and then acting in the downward direction, which is the negative direction here, is in fact mg, and I'll just draw my axis like this and call that the positive y-axis. Again, the summation of the forces in the y direction is equal to mass times acceleration in the y direction. So in this case, I get TR minus mg is equal to m times a. And I don't need to subscript the a's at all, because if I pull the MB on the left down 1 inch, then we'll see, since the rope doesn't stretch nor get slack or anything like that, then when I pull it down 1 inch, the circumference of the pulley is going to turn such that its circumference moves 1 inch, and the rope on the other side is going to lift 1 inch, which means the mass M is going to lift 1 inch. That means the displacement of MB is equal to the displacement of M, and it's actually related through the S equals R times theta to the displacement of the circumference of the circle. Not only that, if I move it down 1 inch in 1 second, then it's going to move up 1 inch in 1 second. That means the velocity on the left is equal to the velocity on the right, and the velocity of the pulley is given by velocity equals the radius of the pulley times the angular velocity. And finally, if I pull down on it 1 inch in the first second and then 2 inches in the second, then that's going to happen to the pulley as well as the mass on the other side, the lowercase m. So that tells us that the acceleration on the right is equal to the acceleration on the left, and that a is equal to r times alpha for the pulley as well. So that's what happens from the rope not slipping, the rope not stretching, and the rope not getting slack. And now you understand not only that, but you also understand why T right and TL are actually different tensions and all that good stuff. So we have four unknowns, but we only have three equations so far. But two of the unknowns are related by, because there's no slipping. So I'll say, since rope does not slip or stretch or dot dot dot, then we can say A is equal to R times alpha, and that's going to be equation 4. Okay, so now I have basically 4 equations. Now, what we can do is I can see that there's a common factor of R on both sides of equation 2. So from this, what I can do is cancel out these two R's on the left with one of the R's on the right, and then the other R on the right can be used to make alpha into A. So when I do that, I now get TL minus TR is equal to 1 half M times, now R times alpha is just going to be A, so I'll write it as R alpha, but then I'll write this as A, so we'll know what to call that. I'm going to call that equation 2 prime because it looks just like 2 and it came from 2, but now I've got 2 with, in fact, A in it instead of the alpha. So with that in mind, I'm going to go ahead and let's say add equations 1 and 3. So if I add equations 1 and 3, the left-hand sides add to give me MBG minus TL plus TR minus lowercase mg. So that's me adding the two left-hand sides. Now I'm going to add the two right-hand sides, but I'm going to go ahead and factor out the common factor of A. So that's going to be equal to MB plus M times A. And now I'm going to call this equation 5. Okay. Now you'll notice I have TR minus TL in the middle of that, and equation 2 has TL minus TR. So I just have the negative of that. I'm going to plug 2 prime into 5. So plug 2 prime into 5. Now when I do that, what I'm going to get is the following. I'm going to have MBG minus mg, and now I'm going to replace tr minus tl with negative 1 half big M times a, and then that's equal to mb plus m times a. So now you can see that I have a single unknown in this entire equation, and I can write it as follows. I can say mb minus m times G is equal to MB plus M plus 1 half big M times A. So now I can say that the acceleration A is MB minus M over MB plus M plus 1 half M. That's a big M there. And actually, I didn't make it very clear, so I want to rewrite that. There's the big M. And then all of that, of course, times G. So we now have the acceleration, and you can see how that acceleration looks just like the acceleration we got for the Atwood machine. The only difference is that now that we're taking into account the mass of the pulley, we have the extra 1 half m term in the bottom, and of course the 1 half is the factor in front of mr squared for the moment of inertia. So that's the very typical thing. If this had been, for instance, a sphere, I would have had 2/5 m there instead of 1 half. If it had been a hoop, it would have been just plain 1 times m there. So we have that. Now I can also find out what alpha is because alpha is just A over R. So in this case, I can go ahead and say alpha, which equals A over R, is clearly MB minus M over MB plus M plus 1 half big M times, now I'm going to multiply by G over R, and that gives me alpha. So now I've got the angular acceleration as well, and that's just from equation 4. So now you can see we've used 1 and 3, and then of course 5 was gotten by using 1 and 3, but we've also used 2 prime, and now we've used 4 as well. So we've actually used all the equations, which is good because if we somehow solved for the 4 variables but only used 3 of the equations, that'd be an indicator that we clearly made some mistake because it's not possible to solve for more variables than you've used equations. You actually have to have at least one equation for each variable, and sometimes having more is not helpful. Now that I have that, I can go ahead and use, for instance, equation 3 to solve for t right, and then I can use equation 1 to solve for t left. So first off, I'm going to lasso equation 1 so I can copy it on the next page and solve for TL. So copy, paste. So there's the ML. Now I'm going to copy equation 3 over to there. Copy, paste. Now I did something bad with that last one. I just saw it moved way the heck over there. Maybe, oh, nope, it definitely stayed over there. Well, that's not helpful. Let's see if I can go back and, there you go. Did the other one stay? Ah, darn it. The other one did not stay. Urgh, make me mad. Okay, that's okay. I'm going to do it again. Copy. Now, I'll go over here and say paste, and I'll put that over there. And then, of course, what we need is the acceleration A. So I'm also going to copy that formula over just so we'll have it. So here we go. Why is my lasso tool not working all of a sudden? Copy, and I'll paste it right in between. So we got that. Now, first off, I suggested TL should be larger than TR, so let's go ahead and solve for TR first, and then we'll compare. So first off, from 3, we have TR is equal to M times G plus A, like that. And that's equal to M times G plus M times A. So now I'm going to take the A and distribute it, excuse me, I'm going to take the M and distribute it through A above. So that's going to be M times MB minus M times M, that'd be M squared, divided by MB plus M plus 1 half of big M, and all of that times G. So now you see we have a common G. And of course, what I want to do is get a common denominator. So I'm going to multiply the left fraction, top and bottom, by MB plus M plus 1 half M, and carry out that arithmetic slash algebra. So this is going to be, I'll just leave the G out to the side just to save me a little writing. So this is going to be M times MB plus M squared plus 1 half M times big M. All of that is going to be divided by the new denominator, which is MB plus little m plus 1/2 of big M. Now the other fraction luckily had a plus in front of it, so I don't have to worry too much about screwing that up, but it's going to be plus M times MB and then minus M squared, and the G is all out in front. We can see that the M plus MB and the MMB is going to add. So these two add together to give you 2, but you can also see that the M squared minus the M squared is going to cancel out. So I can finally say that the tension on the right hand side, which is supposed to be the smaller of the two, is going to be, in fact, 2M, and I'm going to leave the MB off to the side because there's a common factor. Actually, I can't because I got it there, so I'll just leave it here. 2MB plus 1/2 MM divided by MB plus M plus 1/2 big M times G. Now I'm going to make that just a little bit simpler by grouping something with no units next to something with units. And what I see is what I was trying to do was pull out that MB, but I didn't have a common factor of that in both terms. So I'm going to use the lowercase m. So now what I'm going to have is 2MB plus 1/2 M over MB plus M plus 1/2 big M, all of that times lowercase mg. So that's our tension in the right, and now all I got to do is use a similar technique to solve for the tension in the left. This line wasn't supposed to be there, so I'm just killing that. So let's now try to calculate T left. So from 1, I can see that TL is going to be equal to MBG minus MBA. So that's obviously a common factor of MB times G minus A. So I'm going to write this as MB times G, because I'm going to have a common factor of G in it. Uh, and now I'm going to say MB. Now I'm going to plug in the A that I had, and the A that I had was MB minus lowercase m divided by MB plus lowercase m plus 1/2 big M, and all of that times G. So again, I need to get a common denominator, and obviously the denominator we have is the one that I want. So I'm going to do that and say M, I'll pull out the G out in front again like I did last time. So the G's out there. Now I'm going to say MB times MB plus M plus 1/2 M over all that's going to be MB plus M plus 1/2 M. Now in this case, we actually have a minus after it, so I've got to make sure I distribute that minus. So this is going to be minus MB times MB minus M, like that. And then, of course, the G's already outside. So I can continue on with this by distributing. I got the G out in front. That's going to give me MB squared plus MB plus 1/2 MBM minus MB squared. Minus times minus would be plus MB, like that. And then all over top of that new denominator, MB plus M plus 1/2 big M, like that. In this case, you can see that I still get the 2m MB term. So this one and this one's going to add together to give you the M. But in this case, we see that the MB squared minus the MB squared is going to cancel out. And now I'm going to get 2m MB plus 1 half MB M. That takes care of all of the numerator terms, and then all that divided by MB plus M plus 1 half M times G. And that's not quite as pretty as I like, but notice this time I have a MB that can be multiplied or it can be factored out, in which case I'm going to say TL is now just 2M plus 1 half big M divided by MB plus M plus 1 half M, all of that times MB times G. You can notice here that these things look somewhat identical, but the masses that they have in the numerator differ, and the mass that they have multiplied by the sign differs as well. So I've got 2MB plus 1 half M in the TR, but I've got 2M plus 1 half big M in the TL. Not only that, in the TR I have lowercase m times G, and in the TL I have lowercase m sub b times G. So we can see that they are in fact different. Uh, if we actually had used specific numbers, I think you discover that the formula for TL is indeed larger than the formula for TR. Anybody have any questions on that? All right, so that's a more advanced sort of problem, if you will, but it's not that hard. It's just a matter of keeping your wits about you and using all the things that you know. So remember that when they tell you it's basically a rope over a pulley that doesn't stretch, doesn't get slack, and doesn't slip, then you can use S equals R times theta, take the derivative of that, and you get V equals R times omega, take the derivative of that with respect to time, and you get A equals R times alpha. So all of those equations are at your disposal, and that's how that works. So anybody have any questions on that one? All right. Looks like not. Let me go ahead and check the chat. Doesn't look like anybody's typed anything, but just in case. Okay. So now I'm going to go to example 1010, which is a nice example. So let's start off with example 1010. Example 1010 says a heavy pulley. A 15 Newton force represented by F sub T is applied to a cord wrapped around a pulley of mass M equals 4.00 kilograms and radius R0 equals 33.0 centimeters. The pulley accelerates uniformly from rest to an angular speed of 30.0 radians per second in 3.00 seconds. Assume there is a frictional torque. Torque friction equals 1.10 meters times newtons at the axle. Determine the moment of inertia of the pulley rotating about its center. So that's what we're given. So I know the mass of the pulley M is 4.00 kilograms. You really don't need that for this problem, but you can use it to estimate whether the moment of inertia sounds reasonable. The radius of the pulley is, I'm going to go ahead and put that in the appropriate SI units, which would be 0.330 meters. I know that omega 0 is equal to 0, but omega final is equal to 30.0 radians per second. And delta T, the time required for it to get up that high, is 3.00 seconds. That's the time required for it to reach that angular velocity of 30 radians per second. And then finally, the torque due to friction is 1.10 meter newtons. So I'm going to draw the situation we have. So here is our pulley, like that. We have acting on it a frictional torque. Tau friction equals 1.10 meter newtons. Oops, like that. But in addition to that, we have a force Ft equals 15.0 newtons. Now that's a force pulling down on it like that. And by the way, we also know the radius is R0. So in this case, I'm going to start off because I don't have a hanging mass on the left. I don't have a hanging mass on the right. So I don't have a separate free body diagram for those. All I have is a free body diagram for the pulley. So if I draw the free body diagram for the pulley, then it's going to look something like this. Acting on this side is a force Ft. I have acting on it, of course, a torque due to friction that's acting that way. And I can go ahead and say the summation of the torques is equal to I times alpha. And I is something that we're asked for. They specifically wanted to know I equals question mark. So what I have is a torque that tends to rotate this thing counterclockwise. So I'm going to call that direction positive, and that's going to be Ft, which is 15. Oops, I forgot to write that down. Ft is equal to 15.0 newtons. I wrote it on the diagram, but I didn't write it in the equation. So in this case, I'm going to take the 15.0 newtons and multiply it by the 0.330 meters. That's my torque. And that minus 1.10 meter newtons is the total torque. And that's all equal to I times alpha. So computing this, in other words, making these numbers a little simpler, the 15 times 0.33 gives me 4.95. So this is 4.95 meter newtons minus 1.10 meter newtons is equal to I times alpha. So 4.95 minus 1.10 is 3.85. So I'm going to say 3.85 meter newtons is equal to I times alpha, and that's going to be equation 1. Now, I've been given enough information to compute alpha. I know that alpha, for instance, on average is supposed to be omega final minus omega initial divided by delta t. Well, omega final is 30.0 radians per second minus 0 radians per second, and all of that is divided by 3.00 seconds. So the acceleration turns out to be 10.0 radians per second per second. I'm going to call that equation 2. Plugging 2 into 1, we get the following. 3.85 meter newtons is equal to I times 10.0 radians per second per second. So I can now find out that clearly I is equal to 3.85. Now I'm going to break these units apart. I've got a meter, and then a newton is a kilogram meter per second squared. So that's what the meter newton becomes meter squared times kilogram over second squared. And then I'm going to divide that by 10.0 radians per second per second. You can see that the second squareds are going to cancel out, and we end up getting kilogram meter squared per radian, but a radian is just a pure number, so you can throw that away. And our answer is finally 0.385 kilograms meters squared is equal to the moment of inertia for this. Now, if this is truly a cylinder, oops, sorry about that. If this is truly a cylinder, then I, if it's just a flat cylinder, should be 1/2 mr squared. If I compute that, I get 1/2 times 4.00 kilograms. Remember, I told you we didn't really need the 4 kilograms, but if we wanted to compare the moment of inertia, we would need the mass of it. And then this is 0.330 meters squared. So 0.5 times 4 times 0.33 times 0.33 gives me 0.2178 kilograms meters squared. So it's on the same order of magnitude. Uh, this could be different by, for instance, a typical pulley might have a little bit more beef around the outer edges, a little bit more mass around the outer edges, and might be fairly thin on the inner part, sort of like a bicycle wheel. All of its weight is mostly on the rim and the tire and the inner tube and all that good stuff. There's a little bit of weight on the hub, but then the individual spokes of the bicycle wheel are not very massive or heavy either. So that would account for it just by having it not be exactly a cylinder, but perhaps a cylinder with that's a little bit more weighted at the edges. Anybody have any questions on that? So your book gives you a step-by-step approach for solving these problems. I highly recommend that. I just sort of go over it and leave that up for you to read. So please do that. Now we're going to look at example 1011. Example 1011, which I'm going to fit on a new page. Example 10 and 11 says the pulley and bucket. Consider again the pulley in example 1010, but instead of a constant 15.0 Newton force being exerted on the cord, we now have a bucket of weight 15.0 newtons. So W is equal to 15.0 newtons, which implies from W equals mg, M must be 1.53 kilograms. That's something we know as well. So it says, but instead of a constant 15.0 Newton force being exerted on the cord, we now have a bucket of weight W equals 15.0 newtons and mass equals 1.53 kilograms hanging from the cord. We assume the cord has negligible mass, excuse me, and does not stretch or slip on the pulley. Calculate the angular acceleration A of the pulley and the linear acceleration A of the bucket. Uh, that's angular acceleration. I think they meant was supposed to be an alpha, but they wrote A there. Assume the same frictional torque. T friction equals 1.10 acts on the pulley. So we're still going to have T friction is equal to 1.10 meter newtons. And we are going to be asked for alpha equals question mark and A equals question mark. So let me start off by drawing the diagram. I'm going to try to make this one a little bigger. So I'm going to draw the pulley like that. Now, in this case, what I have is a rope, oops, pulling straight down, okay, and a mass hanging here. And this mass is equal to 1.53 kilograms. And we know this radius is R0, and we know that there is a friction torque. Torque friction is equal to 1.10 meter newtons, like that. And that's our problem. So now I've got to do two free body diagrams. So first off, I have this mass right here, and obviously it looks like everything's going to rotate counterclockwise, so I'm going to say the mass going down on the left is a positive direction, and I'm going to say the rotation counterclockwise is a positive torque and therefore a positive angular acceleration. So in order to do that, I'm going to say this is my positive y-axis. I have acting on it a force mg is equal to 15.0 newtons, and then I have acting upward on it a tension T. And that's the only tension to deal with, so I'm going to say it like that. Now, from this, I can reach the conclusion that the summation of the forces in the y direction equals mass times acceleration in the y direction. And that's the only acceleration, so there's no reason to subscript it y. But in this case, I'm going to have 15.0 newtons minus T is equal to 1.53 kilograms times A, and I'm going to call that equation 1. Now I'm going to do a free body diagram for the pulley itself, and this time I'll make the pulley a little smaller just because I can. Okay. On the left-hand side, I have a potentially positive torque, and that is due to the tension on the left-hand side. Notice if you look at these two free body diagrams, the tension on the mass that's hanging is T and it points up, but the tension on the pulley, which is the same one, points down. They are parts of it looks like a action-reaction pair, but the main thing is, according to the mass M, that's hanging, that mass would be falling at 9.8 meters per second if it wasn't for this tension behind it slowing it down. Similarly, if you were the pulley, you would say, hey, I would be sitting here perfectly still if it wasn't for that tension pulling me counterclockwise. So that's the way the tension should look in two different diagrams. In one case, it's acting upward. In the other case, it's acting downward. That's perfectly normal. That's what you want to look for when you're setting up your equations. Now, in addition to that, I also have this tension or this torque friction equals 1.10 meter newtons here. Now I can say the summation of the torques is equal to I times alpha. Again, to keep it consistent with the signs, I'm going to choose the torque due to the tension to be in the positive direction. And of course, remember this distance is R0. So I'm going to say basically T times 0.330 meters minus 1.10 meter newtons is equal to 0.385. I'm going to leave off the units here just because I don't have the room for it. And that all is multiplied by alpha. And alpha is another variable we're wanting to get. I can go ahead and compute this a little better and then I'll number it. So I'm going to say 0.330 meters times the tension minus 1.10 meters times newtons is equal to 0.385 kilograms meters squared times alpha, and that's going to be equation 2. Now, one of the nice things I can do with this is I can divide both sides by 0.330 meters like this, and that gives me now T, ooh, that gives me T minus 1.10 divided by 0.330 gives me 3.33. And notice in dividing it by a meter, that leaves me with just newtons up here. And then 0.385 divided by 0.33 gives me 1.167. Again, add any extra sig fig. That's kilograms meters times alpha. Okay. So now I've got equation 2 in a slightly better form, so I'll call that 2 prime. Now all I got to do is eliminate t and I can solve for a, but you notice I've got t, a, and alpha are all unknowns. So I need one more equation. That other equation I need is a is equal to r0 times alpha, and that is 0.330 meters times alpha, and that's going to be equation 3. So first off, what I'm going to do is plug 3 into 2, into 2 prime technically. And the reason why I'm doing that is because then all of them will be in terms of A instead of alpha. So to do that, what I'm looking at is I'm going to replace the alpha with A over 0.330. So A alpha would be A over 0.330. So now that means I get T minus 3.333 newtons is equal to 0, no, 1.167 kilograms times meters. Now alpha is going to become A over R, so that's A divided by 0.330 meters, like that. And that gives me T minus 3.333 newtons is equal to 1.667 divided by 0.33 gives me 3.535. And now that's just kilograms times A. So let's call this equation 4. And now what I'm going to do is add equations 4 and 1. The reason why I'm adding them is because one of them has a positive t and the other one has a minus t, so they easily eliminate that variable. When I do add them, I get 15.0 newtons minus t plus t minus 3.333 newtons is equal to, now I have a common to both of them, so I'm adding 1.53 plus 3.535. And when I add those two, I get 5.065 kilograms times A. So I can now see that the minus t cancels out with the plus t, and I can see that A is going to be equal to 15.0 newtons minus 3.333 newtons divided by 5.065 kilograms, and 15 minus 3.333 gives me 11.667 newtons divided by 5.065 kilograms. And a newton is a kilogram meter per second squared, so this is going to just leave us a meter per second squared. So I can just say that A is equal to this divided by 5.065. That gives me 4 sig figs divided by 3 sig figs. That's 2.303 meters per second is the acceleration. Anybody have any questions on that part? Okay. Now that we have that, we can go back and figure out what alpha is, for instance. So, for instance, alpha is equal to A over R 0, which equals 2.303 meters per second divided by 0.330 meters. And that gives me uh, alpha is equal to 6.980, and that is radians per second. Remember, the meters will cancel out with the meter, and I'll just get a reciprocal second square, but we can throw in a radian because that's really just a pure number. And now I have alpha as well. They didn't ask us for the tension, but of course we could always calculate that. If we wanted to, I would probably take probably equation one or equation one will be fine. So from equation one, I get from equation one, I get 15.0 newtons minus 1.53 kilograms times A, but we just figured out A was 2.303 meters per second. And then all of that is equal to just plain T. So we get that T should be 15 minus 1.53 times 2.303. That gives me 11.48 newtons is the tension. Now, notice that tension is less than the 15 newtons that the block weighs. So that means the block will clearly be accelerating downward because the tension is not enough to hold it up. Anybody have any questions on that? All right, so that's a couple of different ways we can use kinematics or use dynamics to actually solve a physics problem with regards to rotational motion. I'm going to jump into example 1012 real quick. That one's a pretty quick and dirty one. So let's go here. Example 1012. And what that says is rotating rod, a uniform rod of mass M and length L can pivot freely, i.e., we ignore friction, about a hinge or pin attached to the case of a large machine, as in figure 1024. The rod is held horizontally and then released. At the moment of release, when you are no longer exerting a force holding it up, determine A, the angular acceleration of the rod, B, the linear acceleration of the tip of the rod, and assume the force of gravity acts at the center of mass of the rod as shown. That's a fundamental fact, too. You need to know that whenever we go to do like a free body diagram of a physical object that's not a point particle, then we have to draw it and sort of locate its center of mass, and then any forces acting on it will be acting as if they're acting on that center of mass. So that's a key thing to understand. I'm not going to necessarily give you that quote unquote hint. Assume the force of gravity acts at the center of mass. I expect you to know that from here on out. So just keep that in mind. All right. Here's the diagram that we're talking about. Now we got a little pin here, and we're going to treat this like a very, very small measure is the size of this pin. Okay, in other words, it's essentially zero compared to the length of the rod. And here's the length of the rod. I'm going to say from the center of this pin to the entire length of the rod is a length L, lowercase l, like that. And the center of mass, of course, is L over 2 out to say here. And what we're assuming here is that the weight of this rod, which is big M, and therefore its weight is mg, and I'm also going to say that this rod has a mass of m. Okay, so this is the body. This is how it's going to work. We're assuming actually that even the way I have this pin drawn, it actually won't work because it can't fall all the way down. Later on, we're going to solve the problem as if the rod is sitting like this and it falls all the way down. You can see this one's going to fall like about there, and then the side of that rod is going to hit the wall. But that's okay because we're only trying to study it at the instant I let go of it. So right now you can imagine I'm holding up the right hand side with a force just big enough to keep it rotating. And what they want to know is what is the acceleration of the tip of that and the angular acceleration as well. So I'm going to go ahead and say the summation of the torques is equal to I times alpha. And in this case, the only torque we have is really the weight acting at a distance L over 2 from the center of rotation. So I'm going to say that that is a positive torque, and it's M times G is the force. And then notice it's perpendicular to the lever arm vector being this. And you see that they're perpendicular. Since they're perpendicular, the R cross F just becomes R times F. So in this case, the F is mg and the R is L over 2, like that. And that's the only torque acting on it because we're ignoring the friction and any kind of stuff like that. That is all equal to the moment of inertia of a rod rotated about its end, which I derived last time. So we know the moment of inertia is 1/2 ml squared, and then times alpha. So right from here, we can see that the M cancels out with the M. We can also see that the L cancels out with one of the L's, and the 2 in the denominator cancels out with the 2 in the denominator over there, so that finally I can say that the angular rotation is in fact G over L. Yeah, that looks right. So the angular acceleration is G over L. Oh, sorry about that. That 2 over there is not a 2. That's supposed to be a 1/3. So that's why I was getting a number that I didn't recognize. Sorry about that. Everybody, make sure you correct that. I wrote it all correctly until I wrote the 1/3 over there. For some reason, I wrote 1/2. So this one's L over 2. This one is 1/3. Sorry about that. So now you can see that I get alpha is equal to 3/2 G over L, and that's the actual angular acceleration of this. That's not necessarily that big of a deal, and I'm certain y'all don't necessarily know anything's weird about that, but what is weird is when I calculate the acceleration at the end. We know that A, let me write it in blue, A is equal to L, and that's A of the tip, is equal to L times alpha. So that means that A of the tip is equal to L times 3/2 G over L. You can see that the G cancels out, and we get A tip is equal to 3/2 G. Now, you might not realize it yet, but 3/2 is 1.5. So what we're finding is this object is falling due to gravity, but the tip of it's actually falling at a faster rate than 9.8 meters per second every second. And that's because the mass acts like it's all at the center of mass, and that's what's dictating the torque. But the velocity is twice as big at the actual tip than it is at the center of mass. So you can actually get something accelerating at a rate quicker than gravitational acceleration. I suspect that's the reason why so many people die every year from trees they cut down. The upper part of the tree comes so much faster than they expect that they end up getting hit on it. But that is also a common thing. If if you ever see someone using like a bulldozer or something like that to knock over a chimney or a smokestack, what you'll inevitably see is the chimney starts to fall or something, and then it'll break somewhere along here. And that's because they've designed the structure to handle some lateral load. You can't just build things in public nowadays because we got laws and codes and things like that where you have to account for a lateral loading, which could be from wind or it could be from earthquakes shaking back and forth. And it turns out that when you do that calculation to figure out how much you need to respond to, it's often on the order of 1 g of acceleration. So these things are meant to withhold up to around 1 g in most cases, but when they start to fall like that, their acceleration is greater than a g, and therefore they break in half. So, anybody have any questions on that? Now, that one's actually a bit difficult. We don't know for sure whether the acceleration is a constant. We know at least the initial acceleration is a constant, but it actually turns out that it could depend on theta, the angle at which it rotates, and stuff like that. So we can't just apply kinematics and all that good stuff and go working it out to figure out what the velocities are. But what we can do is we can realize that now that we've introduced rotation, kinetic energy is not just 1/2 mv squared, it's 1/2 mv squared plus 1/2 I omega squared. Notice that I've used all the rotational analogs. The rotational analog of mass is I, the rotational analog of velocity is omega, and you can see that that's pretty much what's been done here is I replaced the m with I and I replaced the v with omega, and now we treat this as if this part is the kinetic energy of the center of mass translating, and so it's called translational motion. And then this is the kinetic energy associated with rotation. So if you have an object that's both moving and rotating, like rolling or something, then you not only have the kinetic energy associated with it moving 1/2 mv squared, you also have a kinetic energy associated with it rotating. So your book goes on to do some more problems like this, and I wanted to work out a couple of them for you. I'm skipping the parallel axis theorem. I'm not skipping it in the sense that we didn't cover it. We already covered it. I'm just skipping that section because I've covered all that material already. I'm going, and by the way, the perpendicular axis theorem I'm omitting. You guys don't need to use that either. It's a little bit more complicated, but the parallel axis theorem is certainly fair game. So I'm jumping on to section 10.8, which is the rotational kinetic energy. And I'm going to go to example 1016. Now, 1015 was really good, and I did work that earlier today, but I'm running out of time. So it's very simple. It's straightforward. You're just calculating the moment of an, or excuse me, the kinetic energy of a big rotating disk that has a mass of 80,000 kilograms. We're going to skip that because it's fairly trivial. And I'm going to 1016, which says a rotating rod. A rod of mass M is pivoted on a frictionless hinge at one end as shown in figure 1030. The rod is held at rest horizontally, then released. Determine the angular velocity of the rod when it reaches the vertical position and the speed of the rod's tip at that moment. So this is where we couldn't do what I just finished telling you we would like to do. We'd like to figure out what the velocity is at the end and that sort of thing, but we don't know anything about the acceleration. We have to solve a differential equation. That'd be kind of ugly. So this is an alternative way of doing it. I'm going to say basically we have a corner right here, and mounted on that corner is a little axle. And then I have a rod just like I did before. And of course, this rod has a length L and a mass M. And then if I go over a distance L over 2 to the geometric center, then that would be the center of mass. And of course, that's where we're going. We're going to allow this thing to drop so that it ultimately ends up in this position, hanging down like this. And now the center of mass is down a distance of L over 2 from where it was before. So using my energy methods, what I know is U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Remember, this is the way that I do it. In this case, we don't have any fathers giving any initial energy to the system. We don't have any springs being compressed to project it out. Oops. So this W out is also zero, and we're ignoring air resistance and friction, which might be a result of the actual axle. Not only that, I'm going to assume that the potential energy at the bottom is zero, so I'm going to say that part zero, and I'm going to say the kinetic energy at the top is zero because it is zero. We're allowing it to drop. So, in using conservation of energy, we know that the mass of the rod is m, gravitational acceleration is g. Remember, potential energy is mgh. I'm going to call this y equals zero so that the potential energy was zero finally. That's totally why I did that. So, I've got mg times L over 2 is the initial potential energy, and that's equal to the final kinetic energy. Now, in this case, the object's not translating, it's just rotating about an axis. So it's only 1/2 times 1/3 ml squared, because that's the moment of inertia of a rod rotating about its end. So that's 1/2 I and then omega squared, like that. Now, what we can see is the M cancels out on both sides, but we can also see that the L cancels out with one L over here, and that's sort of helpful. But we can go ahead and calculate what the angular velocity will be at the end, and what we'll see is we're going to get G times 1/2 is equal to 1/2 times 1/3 times L times omega squared. You can see now that the 1/2s are going to cancel out as well, and I can get that omega is equal to the square root of 3g over L. So that's what the angular speed of it is. Omega equals the square root of 3g over L. Now we want to know what the velocity of the tip is, and v tip is equal to L times omega. So in this case, we can say V tip is equal to L times the square root of 3g over L. I can pull the L inside of the square root, it'll become L squared, and then I get the square root of 3gl. So that V tip is equal to the square root of 3gl. Again, you can see that that's a little faster than we'd expect. If we just dropped an object from a height of L over 2 and let it fall to zero, we would end up getting a velocity of the square root of 2 times g times L over 2, which would just be g times L. But in this case, we got the square root of 3 times larger than that, so it's 1.73 times faster than it would be if we just dropped the object. So again, you can see how the torque acting on a part that's not the very end of it, but is the center of mass, can make the end go quite a bit faster. Anybody have any questions on that one? All right. So the rolling without slipping is that V equals R omega thing. So I kind of want to work example 1017, but I really need to work the next example a little bit more. Uh, well, let's go ahead and do example 1017. What we have here is a sphere of mass m being allowed to roll down an incline without slipping. So here's a mass m, radius r, and what we're going to do is use energy methods to figure out exactly what its speed will be at the bottom. So U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Now, in this case, we're saying it's rolling without slipping. Rolling without slipping can't be done unless there is friction, but at the same time, we're ignoring the energy losses due to friction. So, just want to point that out. The work in, the work out, and the E loss are all going to be zero. I'm going to say the final potential energy is going to be zero. And of course, it started from rest, so the initial kinetic energy is going to be zero. That means what I have is big M times G times H is the potential energy, and that's equal to the final kinetic energy. But this time the ball is actually rolling, so it has a 1/2 mv squared, plus it's rotating, so it has a 1/2 I omega squared. So 1/2 m times v squared plus 1/2. Now, for a sphere, the moment of inertia is 2/5 mr squared. So I'm going to write that 2/5 mr squared times omega squared. And then rolling without slipping, that dictates that v is equal to r times omega, like that. So we're going to make use of that. And specifically, I can now see that there's a common factor of m on all the terms. And I can carry this on and say g times h is equal to 1/2 v squared. Notice the 1/2 and the 2/5, the 2's cancel out, so I get 1/5 r squared omega squared. But notice r squared omega squared is just v squared. So this says GH is equal to 1/2 plus 1/5. I'm going to get a common denominator of 10. So this would be 5 over 10 plus 2 over 10 times v squared is what happens here. So I get GH is equal to 7/10 v squared, or v is equal to the square root of 10, of 10 GH over 7. You know that would normally be the square root of 2GH, but 10 over 7 is actually a little smaller than 2. So that means as a result of this ball rolling without slipping, it's not going to go down as fast as a object sliding down the incline with no friction, because that velocity would have been the square root of 2GH. So, with that in mind, we now know what the velocity is. We can figure out that the angular velocity, of course, omega, is v over r. So that's going to be the square root of 10 gh over 7 divided by r. So you could basically just say that omega is equal to 1 over r times the square root 10 gh over 7 if you wanted, and that would be fine. Now, the other problem that I really wanted to do, and this is the most important one, we'll leave all the other stuff to it, but this is example 1019. And what we're trying to do is solve the same problem, only this time we're trying to do it with dynamics as opposed to conservation of energy. So we're going to have an initial height h, and we're going to have an angle theta like that. And what we have is a ball of radius r rolling down an incline without slipping. And what we need to figure out is what is the friction force and all that good stuff. So the force acting on it actually acts at the center of mass. So this is mg acting that way. However, we can tilt our coordinate system to make this the x-axis and this the y-axis, and then we can break this force up into mg cosine theta, because if this angle right here is theta, then this angle is 90 minus theta, and this angle is also theta. So this is theta here, and then we also have this force right here, which is mg sine theta. We also have a normal force, Fn, that way, and we have a friction force this way. So the summation forces in the y direction equals mass times acceleration in the y direction. Of course, this isn't bouncing on the incline, so in this case we get Fn minus mg cosine theta is equal to 0, so the normal force has to be mg cosine theta. That's potentially helpful, so I'm just going to box it off. Now the summation of forces in the x direction equals mass times acceleration in the x direction. In this case, I'm going to have mg sine theta minus the friction force is equal to m times a. So I'm going to call this equation 2. I'll call this over here equation 1. And now I've got to do the summation of the torques. Now, this is an accelerating reference frame because I'm taking the reference frame riding with the ball, so I have to use everything about the center of mass. So the summation of the torques about the center of mass is equal to I times alpha. In this case, I've got only the friction forces acting, and the friction force is tending to rotate it in a clockwise direction, which I'm going to call the positive direction. So in this case, I've got the friction force times the R, because it's perpendicular to it. So the friction force times R is the only torque that's acting, and that's got to equal 2/5 mr squared times alpha. But one of those r's times alpha can actually be a. So if I cancel this out, then what's left here is just a. So that tells me my friction force is 2/5 m times a, and that's going to be equation 3. That'll come in handy. We're going to need that in a second. Now I can plug 3 into 2, and that gives me mg sine theta minus 2/5 ma is equal to ma. So we can see there's a common factor of m now that all cancels out. And now we can say g sine theta is equal to 1a plus 2/5 a. That'd be 5/5 plus 2/5. That's 7/5 ma. So that means, oh, no more a, no more m was there. So this is just 7/5 a. So that means a is going to be equal to 5/7 g sine theta. That's our acceleration. Of course, our alpha is r times that, or excuse me, our alpha is a over r. So in this case, alpha is going to equal 5g sine theta over 7r. And that's going to be our angular acceleration. And more specifically, our friction force, F, is equal to 2/5 m times A. And we figured out A was 5/7 g sine theta. So you can see now that the friction force is going to be 2/7 times mg sine theta. And you could even go along and, divide out the normal force, and you'd find that the coefficient of friction would be 2/7 mg, or 2/7 times tangent theta, if I remember correctly. But that's it. That was the last problem I wanted to work for this chapter. We're now finished with chapter 10. Next time we'll start chapter 20. I already set the homeworks back. Some I think I sent the homework back to tomorrow night, but let me double check on that. I'm probably going to set it back to a little later still. But you guys are free to go. Chat me your first and last name if you haven't done so already. Thanks for coming, and I'll wait here till the last person leaves in case anybody has any questions. Yeah, I'm moving it from 414. What the heck? I'm just going to go ahead and move it to the 19th. Do not wait till the 19th to do it because you have an online test due on that time, probably. You definitely have those extra credits due at that time. Anybody else have any questions? All right. That's it. See you, everybody. Bye bye.